Hi, my name is Edward Bluerock, and I'm going to give a talk on the ontology for the semantic enhancement, database definition, management, and revision control. This talk is based on ChemConnect, which is actually a case study for a web application for the chemical and scientific instrumentation domain. It actually uses Google Firebase and Firestore, which is a NoSQL database, and blob storage. The motivation of particular importance for the scientific community is fair data management concept, data management plans, and importantly is the traceability, accountability, and the validation of scientific data. This talk will emphasize the role of the ontology in this system. One role of the ontology is semantic enhancement of data objects. This is done through annotations, which are human-readable, and also positions in the hierarchy of other objects to give a relationship or interaction between the ontology objects. Another role of the ontology is database object specifications. So all the data objects have a corresponding ontology object, and in fact the ontology is used to create and manage these data objects. For the data objects within the software, which is Java programming, are actually JSON objects, and these JSON objects are derived directly from the ontology objects. One role of the ontology, particularly important for scientific computing, is domain-specific templates of information. I won't be talking about that too much in this talk, though. One use of the ontology, which I will emphasize in this talk, is using the ontology to drive the software. In other words, a lot of the information, generic information, or I call static information, would be in the ontology, and the software, which is to be more generic, will use the ontology to decide how it should react to data object manipulation. We will see examples of this. So as you can see, the ontology has many roles within ChemConnect. Now I will proceed and give you a couple of examples of the different types of uses of ontologies within ChemConnect. This slide illustrates the ontology program structure. What I want to emphasize in this slide is the ontology is the basis of all the parts of the ChemConnect system. You can see the ChemConnect system has three basic parts. The interface, which can be a web interface or graphical user interface. The background services, which is basically in Java. And then the database portion, or the blob storage portion, which is in Google Firebase. The ontology defines all the objects used within all these sections of the ChemConnect system. With this slide, I'd like to emphasize the interaction between the ontology, the program, and the database. On one side, on the right side, you can see the static information, meaning the data object specification. On the left side are actually the instances of the data objects, which are used in the program and also in the database. On the ontology side, the data objects are based on the DCAT ontology. The top database object is based on the DCAT catalog. This is the specification of the objects and used in the system and what is stored actually in the database. One of the elements of the catalog, and there could be several, are the catalog records. The simplest component is actually the component, which is basically strings, numbers, and simple objects. So the catalog is made up of catalog records and components, and catalog records are just made up of components and maybe other records. The catalog specification is actually the basis of the JSON object, which is actually the main data object within the program and within the database. The program actually manipulates the JSON objects, and it's these JSON objects that are actually stored within the Google database. So here we see on one side the ontology gives the data object specification, and on the programming side are the instances of the data objects using this specification. Now I'd like to talk about the ontology use in the documentation and specification. In other words, for semantic enhancement. Here's an example of a database catalog object. One use of the ontology in ChemConnect is catalog object specifications. And here we see a catalog object that's made up of catalog records, and components. The catalog object is a hierarchy of records and components. Here we see the database person catalog object that has several records in it. Here we see a record or subobject of the catalog object called personal description, and in itself also has a catalog object. The next catalog object, or the next catalog record, is a record itself, but it consists of a bunch of components, and you can see these by the DC terms has part. And here we see a component, which is the tree leaf of the catalog object hierarchy. Is a given component, is a given name, which can be basically a string. And this hierarchy of catalog objects, catalog records, and components make up the catalog object itself that is stored in the database or manipulated by the program. The data objects within ChemConnect are semantically enhanced by, for example, their appearance in a hierarchical organization. All the basic objects like catalog objects, or even processes, or even transactions, are basic concepts which are used by the objects, are all in a hierarchy of objects. Here is the hierarchical organization of processes. They are all subclasses of the software agent from Prove ontology. A special class, data object manipulations, has several subclasses. And then a more specific version of this process is the interpret text block, which are many ways to interpret the text block. This hierarchy gives semantic enhancement to where the process lies in the total scheme of things. Here we have an example of documentation and specifications, and we see the ontology has a one-to-one correspondence with objects within the code, the Java code. Here we see an example of a subclass of software agent which is called the interpret text block. And we see the subclasses of the interpret text blocks are actually the enum possibilities within an enum structure of Java. This gives an added specification, but also an added documentation and a context for all objects or processes within the ChemConnect system. Here we see an example of interpret text block, which is a subclass of software agent. The interpret text block actually corresponds to an enum within Java. And the possible contents of the enum are actually the subclasses of the interpret text blocks. And here we have a means of documenting or putting in context all the sub-processes within the system. Having a one-to-one correspondence between the ontology objects and Java code gives more documentation along with the specification of the processes. It also gives the processes a context and see where it lies in the grand scheme of things. The RESTful services in the background process are also specified and documented within the ontology. The RESTful services are all the subclass of the database services base, which is also in turn a subclass of the software agents. All the RESTful services are subclasses of this class. Here we see a specific service with its definition. The definition includes what should be the input and what should be the output of the service. The service definition basically has two parts. The input, which can be several definitions of components or records or even catalog objects, and the output. The output is specified as has output. Here the input has part, which means it's a component, which means it's a single string as an input. There's a one-to-one correspondence between the ontology service and the Java code. Each ontology service has specific core code in Java. Now, around this is this generic way to process services, and eventually, given the service name, it will arrive to the proper code segment. The JSON object as input to the generic process server within the system has a standard form. The service gives the name of the service, which corresponds to the Java code, which also corresponds to the definition within the ontology. The input is specified by the ontology, and that is what is expected by the service. All RESTful services in the system have a single JSON object as the input. One of the items within this JSON object is the service name, or which service should be called. In this case, it's dataset create object template. The next set of items can be the input. In this case, it is a single string, as we said by the has part before, as to generate a activity catalog database person creation. The output of the service is also a JSON object. In this case, the service should create a template for activity catalog database creation, which would be a catalog object which looks like the following. So here we see that the ontology served as a specification of the services, in other words, what to expect when you call the service, and also documentation, in other words, giving it some semantic context. In the next set of slides, we're going to show another use of the ontology as the core of a data-driven processes. This will promote writing generic Java code and to maximize process-specific information in the ontology and to minimize process-specific code. Transactions are the key to object manipulation. There cannot be any object manipulation of catalog objects within a database without going through a transaction. There's a one-to-one correspondence between a transaction and a output catalog object. Each transaction produces a catalog object. And of course, to create a catalog object, you have a set of prerequisites. The transaction handles this by having a set of prerequisite transactions that must occur first before the catalog object can be created. This gives a clear traceability of the origin of catalog objects. As with other objects within the ontology, transactions are within a hierarchy of events or transaction events. The transaction definition itself has several parts, specifying the input, the prerequisites, and the output. Here we're going to show an example with the catalog object creation event. The requires field of the definition says which transactions are necessary to perform this particular transaction. These are the prerequisites. In addition to the prerequisites transitions, or the catalog object associated with the prerequisite transactions, is a set of supplementary information that may be necessary to create the final object. The result of the transaction is a catalog object which is stored in the database. there's a one-to-one correspondence between the transaction and the output object. The use of transactions allows the traceability of a particular catalog object. In other words, what was needed to create that catalog object and how was that catalog used later. The following set of slides will show how this transaction information is used by the code to create new catalog objects. Performing a transaction involves the ontology's interaction with the interface, with the database, and the transaction process here shown, which is actually the Java code, core Java code to create the data object. From the ontology, we have the transaction definition. The transaction ontology object only specifies the prerequisite types. The specific prerequisites have to be extracted from the database. Given the prerequisite types, the set of transactions that could be possible candidates for this particular operation will be given. The user interface is used for the user to select which of these possibilities is the actual transaction we want to use as input. The selected prerequisite transitions will be the input to the actual transaction process, which is the specific Java code having to do with this transaction. The interface is also used using the template of the supplementary information to give additional information that is needed by the transaction process. The supplementary input information is also an input to the transaction process. Given the supplementary input information and the specific transactions, prerequisite transactions, we can now perform the transaction process. The output of the transaction process is given by a catalog object template from the ontology. The actual output of the process is an instance of this catalog object. This catalog object is then stored in the database. Once the catalog object is created, it will also be used to create some RDFs. Within the catalog object template, there is an RDF specifications. These are used in conjunction with the actual catalog object that was generated to be able to generate database RDFs. The result are database RDFs. How exactly these RDFs are generated will be shown in the next couple of slides. We have just shown how the transaction definition was used in conjunction with the interface and the Java code and the database to create database objects. The only code that actually is specific to a specific transaction is the transaction process. All the other code or all the other interactions were done automatically and is generically the same for all transactions. Given a catalog objects, database RDFs are automatically generated from the ontology template. The subject, the predicate, and the object making up the RDF will be extracted from the generated catalog object. In the catalog definition, there is not only the set of records and components that the catalog object is made up of, but also a mapping relation which says how to generate RDFs. Within the catalog objects and its sub-objects, whenever a SCO's mapping relation is found, this is the signal to generate a database RDF from the information found in the catalog object. For example, this mapping relation points to RDF person family name, which will make an RDF which will link the family name to the catalog object. The ontology RDF definition has several parts which actually specify specifically which object should be extracted from that catalog and put into the RDF database RDF. The prov entity specifies the subject of the RDF. In this case, it says family name. The type family name is searched for within the catalog object, and when it is found, that will be the value of the catalog object of that particular component will be used within the RDF. The information is extracted from the catalog object and put as the subject of the generated RDF. The RDF specification name will be used as the predicate of the particular RDF generated. This string name will be used as the predicate within the generated RDF. In the RDF specification, the school's member specifies what should be used as the object of the RDF. As before, the catalog object is searched for this particular key. As before, the catalog information is extracted and put into the object of the generated RDF. In this way, an RDF with a subject, predicate, and object corresponding to the catalog object is automatically generated. This whole process is the same for all catalog objects, and so basically all one has to do is put in ontology objects for the mapping relation and the RDF specification, and the RDF will automatically be generated. In this talk, I've outlined several roles of the ontology. For example, semantic enhancement by giving a context and information about each object within the ontology. Database object specifications, in other words, having a one-to-one correspondence between data objects in the program and the ontology. And also the way the ontology can be used to automatically generate objects or catalog objects given definitions within the ontology. Thank you very much for listening, and if you want some more information, I've given some links below.